Welcome back, everyone. So let's do another problem. So in that case, we have a diode oriented in the upward direction, and there is a DC voltage source. So as I said before, we're going to start by observing the half cycle for which the diode is forward bias. So let's say this is our input signal VI, 10 volt, 0, T by 2, capital T, 3T by 2, minus 10 volt. So this is our signal. So notice, if you keep our signal to my left, diode appears to be anti-clockwise direction. So that means for positive half cycle, diode appears to be reverse biased, but the negative half cycle, diode appears to be forward biased. So in that case, we're going to ignore the positive half cycle. Instead, we're going to start our analysis from negative half cycle. That means, so VI less than 0, and diode is forward bias. Now, in that case, we're going to consider, let's consider the diode is not ideal diode, diode is silicon diode. That means we're going to consider constant voltage drop model. When the diode is on, we're going to replace the diode at 0.7 volt. And one thing you should know, so we're going to analyze the clamper network for two half cycles. So in that case, at first, we're going to analyze the clamper network for negative half cycle. And then we're going to analyze the clamper network for positive half cycles. So each cycle, we're going to determine two things. Number one, we're going to determine voltage across the capacitor, and then V0, output voltage. So first of all, we're going to analyze from that half cycle for which diode is forward biased. So the diode is forward biased for negative half cycle. So let's say this is our polarity. Okay. And for that, diode appears to be forward biased. So diode is forward biased. Okay. So as the diode is forward biased, the current is flowing through the diode. The current is flowing through the diode. This is that. The real current always flows from positive terminal to negative terminal through external circuit. So as the current is flowing through the diode, it is going to flow through the capacitor. As the current is flowing to the capacitor, we know that capacitor is charging up, and the capacitor will be charging up instantaneously because the tau 1 equals to 0. So the capacitor will be charged up instantaneously, and it's going to develop a voltage across the capacitor, which we call Vc. And then we already learned that we have to select the polarity of the capacitor, and we are going to select the polarity of the capacitor voltage such that the current, the terminal through which current is entering will be our positive terminal, and terminal out of which the current is leaving will be our negative terminal. So now that this is Vc, which is unknown, so let's determine the value of Vc. So for that, we apply a KVL. So minus Vi plus Vc minus 2 plus 0.7 minus 5 equals to 0. So Vi is equal to minus 10 plus Vc plus minus 4.3 equals to 0. So that gives us Vc equals to 14.3 volt. So this is the voltage across the capacitor. So this is one thing we have already determined the value of the capacitor when the diode is, value of the voltage across the capacitor when the diode is on. So next thing we need to determine V naught. So V naught is the voltage across the resistor. So how about the resistor is parallel to the diode and the DC voltage source. So that means we can find out V naught to be plus 5 minus 0.7 equals to 4.3. So this is the value of V naught when the diode is on. Now once the positive half cycle is over, so from there we find out once the positive half cycle is over, then comes the, sorry, when the negative half cycle is over, then comes the positive half cycle. So this is the half cycle we are going to consider. Okay, so this is the half cycle. 0 to t by 2, sorry, 0 to t by 2 to t, 3t by 2, 2. So that means when t is greater than t less than 3 by 2, we have Vi is greater than 0, but in that case, diode is reverse bias. So this is our polarity. Now in that case, since that diode is reverse bias, diode is off. Okay. And the current will be flowing from positive terminal to negative terminal through external circuit. So that means the capacitor will no longer be charged because the direction for the current, direction of the current has reversed. The capacitor charging was, polarity was this. So since the current was flowing in this direction when the diode is on, that's why capacitor was charging. Right now, when the diode is off, the current direction has reversed. It is in this direction, so capacitor is not going to be charged. Instead, capacitor will start to discharge. As you have already learned, we have selected the value of capacitor C and R such that it takes longer time to discharge. So therefore, we're going to find when the diode is off, Vc is equal to 14.3 volts. So whatever the value that we have found, 14.3 volt. Now I want to determine V naught when the diode is off. For that, we are going to apply KVL. So plus Vi plus Vc, assuming that it is positive, so minus V naught is equal to 0. Vi is equal to 10 plus 14.3 is equal to V naught. V naught is equal to 24.3. So let's draw it. Let's draw it. Let's say, so we add another axis. So V naught. So let's use different in color. Okay. So 0 to t by 2 interval undetermined. So we're not do anything. We're not going to do anything here. T by 2, then t, then 3t divided by 2. Okay. So t by 2 to capital T, we have 4.3. So let's say 4.3. and then T2 3T divided by 2, that means during this interval we found 24.3. So 24.3 volts. So 4.3 to 24.3. So that means the peak to peak difference is 24.3 to minus 4.3. You see what we did? As if we grabbed the signal and pulled it up by 10 volts, 14.3 volts. So therefore, 4 minus 10 has become 4.3, and 10 has become 24.3. So that means we have pulled it up by 14.3 volt. So that is our clamper.